Each element has a spot on the periodic table containing information about its name, number of protons, and mass. The elements are organized across and then down the table by the number of protons in the nucleus. Hydrogen has 1 proton, helium 2, lithium 3, beryllium 4, boron 5, carbon 6, and so on. In addition to being ordered by atomic number, the organization of the elements into rows and columns captures repeat patterns in the properties of different elements. In fact, the name periodic comes from the periodicity in characteristics of the elements. It is this periodicity that drives the logic for starting the third row at 11 and the fourth row at 19. And just by looking at where in the table an element is placed can tell you something about its properties and the type of chemical interactions it will undergo. On the far right are the noble gases. To the left of those are the nonmetals. Moving further left are the metalloids, which have a mix of properties between metals and nonmetals. With the exception of hydrogen, the rest of the table is made up of the large metals group. This group is broken down into subcategories: the metals themselves, the transition metals across the middle, and the alkali metals and alkaline earth metals on the far left. There are 4 broad regions of the table that represent the organization of electrons orbiting the nucleus, with each region representing a different type of orbital. The 4 orbital types are s, p, d, and finally the lanthanides and actinide series, which are the only elements with electrons in their f orbitals. Each of these orbitals have different characteristics, and it is the behavior of the electrons in these orbitals that give different groups of elements distinct chemical properties. Starting from knowing that electrons orbit the nucleus of an atom in a finite number of specific orbitals, we can explain the organization of the periodic table by adding some additional information. First, the specific orbits that electrons can be in are organized into s, p, d, and f orbitals, and that these orbitals can be further grouped by shell. Not all shells have all orbital types, but they do occur in predictable patterns. Each orbital can hold 2 electrons. There is 1 s orbital per shell. If a shell has a p orbital, there are 3. If it has d orbitals, there are 5. If it has s orbitals, there are 7. And as electrons are added to an atom, they fill the shells and orbitals in predictable ways. The Bohr model shown here is not an accurate representation of how electrons move around the nucleus, but it does help illustrate how electron shells fill. Looking back at the periodic table, each row represents a shell. Moving from left to right along a row is adding an electron to a shell. In the rightmost column are elements with full outer shells. These are the noble gases, and their full outer shells make them very stable and chemically inert. Moving down the table from row to row adds a shell. The first row has only a single s orbital and can hold 2 electrons total. The second and third shells have 1 s and 3 p orbitals, allowing them to hold 8 electrons, 2 in the s and 2 each in the 3p. The fourth and fifth shells have s, p, and d orbitals, allowing them to hold 18 electrons, 2 in the single s orbital, 2 each in the 3p orbitals, and 2 each in the 5d orbitals. Finally, the last 2 rows add 7 f orbitals, giving them the ability to hold 32 electrons each. We can step through the first 2 rows of the periodic table to get a sense of how the shells fill, starting with hydrogen, which has 1 proton in the nucleus and a single electron in the first s orbital. The second element is helium. It has 2 protons, making it want 2 electrons to balance the charge. The addition of a second electron to the first s orbital completely fills the available orbitals in the only and therefore outer electron shell. The element with 3 protons in its nucleus is lithium. The additional electron to balance out the charge of protons is added to the s orbital of the second shell, which is why lithium starts the second row of the periodic table. As we move across the second row, we add 1 proton and room for an additional electron for each additional element. The second element in the row is beryllium, with 4 protons and room for 4 electrons. 2 electrons in the first full shell, and 2 unpaired electrons in the second shell. Next is boron with 5 protons. The addition of a 5th electron gives the outer shell 3 unpaired electrons. Boron is followed by carbon, 6 protons in the nucleus. The matching 6 electrons are the 2 paired electrons in the first shell and 4 unpaired electrons in the outer shell. Nitrogen is next with 7 protons. There are only 4 orbitals available in the second shell, one s orbital and 3 p orbitals, so the addition of a fifth electron to the outer shell fills one of the orbitals, leaving only 3 unpaired electrons. The pattern continues with oxygen. It has 8 protons, 6 electrons in the outer shell, leaves only 2 unpaired electrons. Fluorine has 9 protons and a single unpaired electron in the outer shell. At the end of the second row is neon with an atomic number of 10. All of its orbitals are full. The third row of the table fills much the same way, so that the next noble gas has 18 electrons, 2 in the first shell, 8 in the second, and 8 in the third. The rest of the rows have d and f orbitals in addition to the s and p orbitals, making filling patterns more complicated. But focusing just on how p and s orbitals fill gives us a lot of information about how chemical bonds form. Chemical bonding only involves the electrons in the outermost shell. This shell is called the valence shell, and the electrons in it are the valence electrons. Atoms form chemical bonds in order to get to energetically favorable states. Many chemical reactions occur in order for atoms to balance the charges between negative electrons and positive protons, or to achieve a noble gas state with a full set of electrons in their valence shell.